All right, today we're going to crack the code on the language of measurement. We're diving into this super elegant system that lets scientists talk about, everything from the tiniest atom all the way out to the distance between galaxies. And they do it all with just one simple set of rules.
So, how is that even possible? How can you use the same tools, the same language, to describe something infinitely huge and something impossibly small? I mean, you'd think you'd need two completely different rulebooks, right? Well, the amazing thing about the International System of Units, you'll hear it called SI, is that nope, you absolutely don't.
The absolute genius of this whole system is built on one simple, incredibly powerful idea: the number 10. Everything, and I mean everything, is decimal. You can scale any unit up or down just by multiplying or dividing by 10. No more weird conversions, just clean, logical steps.
What this means in the real world is that your calculations and conversions become incredibly simple. You just attach a simple prefix to a base unit like a meter or a gram, and bam, you've changed its scale instantly. It's all done using powers of 10. Think of it like a universal translator for size.
Okay, so let's start by looking way up at the truly massive stuff. How does a system build units to describe things on a cosmic scale? Well, it all comes down to these prefixes we call multiples.
And what's really cool is that you already know these words. Kilo for 1,000? We see that everywhere. But check out the bigger ones: mega, giga, tera. If you've ever bought a hard drive or a new phone, these are your terms. A gigabyte isn't just some techie jargon. It literally means a billion bytes. A terabyte? That's a trillion. See, it's the same exact system, hiding in plain sight. And here is the secret sauce, the mental shortcut that makes it all so easy. Look at the powers of 10. It goes from 10 to the 3rd, to the 6th, to the 9th, to the 12th. Once you get past kilo, you just keep adding 3 to the exponent. It's this beautifully organized ladder that takes you right up to the immense.
Okay, so we've built our way up to the gigantic. Now, let's use that same logic to zoom all the way down into the microscopic world of cells and atoms. For that, we use what are called submultiples.
We start with milli for 1,000th, pretty common. Then it gets really small with micro for 1,000,000th, and you'll notice that special Greek symbol mu, which is pronounced mu. You see that all over the place in science. And from there, it gets even tinier with nano, think nanotechnology, and then pico.
And this is where you see the beautiful symmetry of the whole system. The exact same jump by threes rule works here too, just with negative exponents this time. You've got 10 to the minus 3, minus 6, minus 9, minus 12. It's the same ladder. We're just going down into the microscopic world. It's perfect logical harmony.
Okay, so we've got our basic units, and we've got our prefixes. But what about measuring something more complex, like area, or volume, or even density? This is where the system gets really creative. We don't have to invent brand new separate units, we just combine the ones we already have, like Legos. Let's start with a really simple one: area. In plain English, it's just how much flat space a surface covers, like the floor of your room. So how will we measure that using the building blocks we already have?
Easy. We just multiply two length units together. For instance, a meter times another meter. The result isn't just a number, the units themselves actually multiply, giving us a brand new, derived unit, the square meter, or meter squared. We literally just built the unit for area from the unit for length.
Now let's see how this concept can, build on itself. What about volume? That's the amount of three-dimensional space something takes up, like how much water is in a bottle.
So, we can take the unit for area that we just made, the square meter, and multiply it by one more dimension of length. A meter squared times another meter gives us, you guessed it, a meter cubed. We've now derived the unit for volume. See how we're building up complexity from these simple blocks? It's pretty cool.
All right, for our last example, let's get a little fancier and combine two different kinds of units: density. It basically tells us how much stuff, or mass, is packed into a certain amount of space, or volume. It's the reason a block of steel is so much heavier than a block of wood that's the exact same size. So this time, instead of multiplying, we're going to derive our unit by dividing. To get density, we just take the unit for mass, the kilogram, and we divide it by the unit for volume we just created, the cubic meter. Our final unit is kilograms per cubic meter. It's as simple as that.
Now that we've seen how to build all these cool units, we kind of need the user manual, right? How do we actually do the math with all these powers of 10?
The great news is, there are just a few simple rules for exponents that you need to know, and you're all set.
And the rules are surprisingly straightforward. If you're multiplying 2 powers of 10, you just add the exponents together. If you're dividing them, you just subtract the exponents. This little trick turns what could be a messy calculation with tons of zeros into simple addition and subtraction.
So what about this last rule, when you have a power that's raised to another power? For something like 10 squared, and then all of that is raised to the third power, the rule is even simpler. You just multiply the exponents. So 2 times 3 gives us 10 to the 6th. Done.
So, let's wrap this up. The whole system is beautifully built on powers of 10. We use prefixes to scale our units up or down, and we've got that awesome jump by threes trick to help us out. We can combine our base units to create new derived ones for basically anything we want to measure, and a few super simple exponent rules handle all the math. It really is a universal toolkit for describing the entire physical world.
Which kind of leaves us with a final thought. This system really does give you the power to define and measure just about anything. So now that you know the rules of the game, what complex property of the universe would you want to figure out how to quantify? Something to think about. Thanks for joining me.